It's okay.
It's going to be amazing. Yes. It's going to be amazing.
That's probably enough drinks for tonight.
That's so cool. It's going to be amazing. It's going to be amazing.
That's probably enough drinks for tonight.
Yes. That's so cool.
It's okay. It's okay.
Yes. That's so cool.
That's probably enough drinks for tonight.
That's so cool.
It's okay.
Yes. It's going to be amazing.
It's okay.
Yes. That's so cool.
That's probably enough drinks for tonight.
And good morning, good evening, good afternoon, good whatever it is, wherever you are. I'm Dave Stokes from Percona, and with me is Marcos Albe. Today we're talking MySQL schemas. I thought a couple of years ago everything was supposed to be you just open a JSON column and pour everything in there. Do we still need relational data?
Oh, no, don't do that. Don't do that, please. And let me tell you, like you started with that. Let me tell you something since you kick-started that. That is the biggest lie in databases in the last decade, I believe. Schema-less databases are a huge, huge lie. There is no such thing as schema-less. On the opposite side, when you are using something like MongoDB, you have to more carefully design your schemas because the cost of doing lookups, the equivalent of doing a join in relational databases on MongoDB is very high, very high. So much so that Tengen, MongoDB Inc., will still recommend you to use embedded documents. But that always makes things more costlier, right? So I don't think that's a very good advice.
Okay. Cool. So, and the number 2 lie in databases for the past decade is it's going to be cheaper every place in the cloud.
Oh yeah, that's that's
Very good.
that's even a bigger one.
Yeah. Okay. So, well, let me turn it over to you and let you expound on schemas.
Yes, sir. Let me please share my screen. Let me find, how do I share screen on this thing? Awesome. Here we are. Share. And let me put this on a slideshow. Oh, can you see my screen, sir? I believe so. Yes. Right. So welcome everybody. We're going to be talking about one of the fundamental things in databases, which is how to properly design your schema. Like Dave was saying, the promise of a schema-less world has been left behind, and now everybody admits that schemas are necessary, and that you might save yourself from doing alter table, but still you have to carefully design your schema to have a good foundation to build reasonable queries. So a database is a system to store data and to later be able to retrieve it and produce some form of intelligent reporting or gathering to perform other actions. So be able to do those queries later in an efficient way, it's important. And for that, we need to properly design the schema. So the first thing you will learn in college, if you do databases course, one of the first things, and so Shashank is asking me if I am sharing the screen. Can you confirm you can see it, David? Shashank, I am. I see you're on LinkedIn. Not sure if that will prevent you from seeing it. I am waiting for David to tell me. I'm sure in YouTube you should be able to see it. Am I right, David? I think I lost David, or he's.
So hold on. Yes, it's on Twitch and it's on YouTube.
Okay, could you share the YouTube link on the chat? So
yes, I will.
Hey, hello, Edith. So the first thing you have to learn is how to normalize your tables, and this is done by following the so-called normal forms. This is a series of rules that help you, that you can easily apply, or that you can apply to your schema design, that were created by James Codd back in the 70s when he came up with the relational databases idea. And it's a set of 6 rules. So 1, 2, 3, boys code rule, and 5, 6. Normally, we only do 1, 2, 3, And perhaps if you have like a very weird situation, you might apply voice code. We're only going to be looking at the first three. And again, these so that when you're designing a schema, you're creating your application, right? It's at the time of the application inception. So you will gather the description, you will gather the requirements, the use cases, and you will extract all the data you want. Like you will, based on that, know the information you want to store on the database, and you will start putting that into so-called entities or relations. And with the relations, you will start then normalizing them. And here we go. So normal forms. The first normal form, each column of a table must have a single value. So no multi-valued columns. A column which contains a set of values or nested records, like a JSON, those are not allowed. So let's see a quick example of how this will be. This will look in real world. Very silly example. I have my table, and I have, I have my table, my ID for this row. I have a name, and I have phone numbers. And in this case, I have two phone. I have two phone numbers. So 555, 888. For Dave, I have only one. And for Peter, again, I have two phone numbers. So how could I look up for a single phone number? Or how could I know if this space belongs to the phone number, or if the space is actually just a separator with the extension for that guy? So the right thing to do is to split this into a users table and a phones table, where you can have, just my ID and the name. And then on the other table, I will have an ID for this entry, and the user ID, which refers to this table, and the phone number. And then I have, for the same user, I have another phone number. Then for Dave, I have his phone number here. And then for Peter, I have 1 and 2 entries. So that way, we can address the phone numbers individually. And this is probably one of the most important things you could do for your database design. Don't embed, the multiple values in a single column. That's against good practices, and it will make your life difficult down the road. Another normal form. Every column that is not part of the primary key shouldn't be able to be inferred from a smaller part of the primary key. Okay, this is more easily shown than explained. So let me try this. I have my table, project assignments, and I have the project assignment has an employee and a project to which the employee is assigned. But in this case, I have the employee name here, and I have the project name here. And I could actually infer the employee name from the employee ID, and I could actually infer the project name from the project ID. So in cases like this, what you must do is actually never have these columns, name and project here. You will have your own table with your employees, and you will have your own table with your projects. And then you will have the single table with a composite primary key, where employee ID and project ID combined are the primary key. And then you will have any other data for that assignment, for example. For in this case, like I was assigned 124 hours to do something. So again, the core concept is I was able to infer employee name from the project ID. So I don't want to have it again here. I will keep it in a table. And if I ever need all this data together, I can use the relationships between employee ID and project ID and ID in the project table and put them together using a join. By the way, this is what, an embedded document like in MongoDB, it will look like this. It will have everything in a single hit, right? Like everything will be in a single document. Like, and again, if you wanted to later, let's say, update my name, why is this important, right? Like, it's important because if I want to update my name later, I will have to look up every row in every table where I have put my name versus being able to update it only in one table. So if I refer to employees via their employee ID, when I want to update something about the employee, I will do so in a single place. And instead of having to go to each table and each row where data about such employee will have appeared. So that is the goal, is to not duplicate data and to have it in a single place, to avoid anomalies, to avoid introducing, your application will later be at the risk of forgetting to update one of the rows or to forget to update one of the tables. So to avoid such possibility, the right way is to apply the second normal form. And here is another one, which is a bit more convoluted to say, but it's not so hard to look at when we see the example. So let's get into it. Third normal form, there shouldn't be a non-prime attribute that depends transitively from the primary key. That's a lot of words, and it kind of hard. It's the kind of things that makes people not want to do databases when they are in college, I guess. So here is again. We have, some books, a books table that is very badly designed. We will see in a second. I wrote a bit about how to barbecue. Dave wrote a Hitchhiker's Guide, and Peter wrote the MySQL High Performance book. So, I have title and format as my primary key, because I could have my How to Barbecue book in hardcover and paperback. So to uniquely identify, I resorted to creating a composite key here. Right away, you can tell Marcos, this is not compliant to the second normal form, because I should be able to infer the price from the format. So that's not in second normal form. But further, the title is tied to the author, and the author country is tied to the author. So the author country is an indirect dependency to the title. And that's the third normal form, what the third normal form wants to avoid. He doesn't want you to have data about this guy on this table, because we could identify this guy via the title, and then later we could identify the country via the author. So the right way to do this is, first of all, apply the second normal form and make title format a primary key in a secondary table, in a separate table. And here we will have the prices. Here we will have the books, and the books appear only once with the author only once, and the metadata about the book. Because the price is not metadata about the book, it's about the format for that book. So second normal form. And because this was primary key, right? Here you can see it's under underlined. It has another line that in schema design, when you're designing schemas, you will normally see that people underlines something. That is your primary key in the table. So I moved out the price. I kept my title and author. The author is not a primary key. It's just an attribute of the book. And then I have a table with authors and their country. And now this table complies to both the second normal form and the third normal form. And again, while this might seem going too far into breaking down things into smaller tables, and while it certainly will imply a bit more work when you're doing your joins, it will really make maintenance of the data itself cheaper. So you will not have to look for the author country in every row and update it everywhere, which is going to be super costly. You will only update it here, which is simpler, centralized, and less costly in terms of actual work done with performance, right? So these three rules, are the bare minimum you want to apply. So these are literally, don't go on to writing your queries before you get the third normal form applied to your tables. So I'm not like, if you have questions, please, share on the chat. I know this is a bit confusing to say the least, and that it takes practice, but it's so important that it's hard to overstate it. So please take a time. There's a plethora of material in the internet. I hope my explanation it's somewhat clear, but please ask away if you feel like. Referential integrity. So referential integrity, it's well, first of all, let's say what a reference is, right? Like when we were looking here, we said, okay, I can have my employee ID and refer to it on the employees table. And I can have my project ID and refer to it on my projects table. And then I don't need to keep my project name and everything else in the project assignments table. The thing is, what if I insert something in the project assignments table with a project ID that doesn't exist, right? Or what if I try to now delete project 99 and I forget to delete the entries in project assignments that were using project 99? So that is the subject of referential integrity, making sure that when we have a reference between tables, a so-called foreign key, so the project ID here is a foreign key to the projects.id column. When I have those, I want to make sure that they are valid, that they will not be created or removed while the parent doesn't exist or while a child is using it. In these relationships, the project ID will be the parent table and the project assignments will be the child table, right? It's pointing to the parent. So referential integrity is about that. I don't want to insert a child row for a value that doesn't exist in the parent table. And I don't want to delete a parent row that still has any child. So we don't want to leave orphans and we don't want to create orphans. That is like an easier mindset, perhaps. So with that in mind, what does referential integrity helps us? So it helps us prevent programming mistakes. Again, imagine you are just creating a form and you let the user insert their own project ID instead of offering them a list of existing project ID. Well, if you don't validate that the project ID exists before, having a foreign key constraint will help you prevent the mistake, right? Like there was a mistake which was allowing the user to insert without checking the project existed. So by having the foreign key constraint, you are having the database do that work for you. So it's helping you prevent programming mistakes. Also, in a way, in a sense, it's a self-documenting schema relationships, because if I see that so this will be embedded in the data definition language for the table. In your create table, I should have included an example here. I can look up one very quickly in a moment. But basically, because it will be part of the table definition, I am looking, oh, this table depends on this other table. And, even if the table names are not obvious, even if I know anything about the system, I will know those two pieces of data are related and that they can be somewhat logically joined, right? They can be combined to form a bigger entity. So that is also quite important because it helps us have more clear understanding of the schema. And also, if you're using a relatively good model entity relationship diagram program, like a piece of software that helps you design your entity relationship diagram, they will usually be able to read the data definition language, and they will be able to automatically generate the links between the tables. This doesn't come without drawbacks. While you were saving yourself from that, doing that lookup, well, you didn't need a lookup before allowing the insert of the project. The database is going to do the lookup for you. And, that has a time cost. Like, it really has to go to disk, look up the page that contains the row you're referencing, and make sure the row is there, right? So it's going to look up through an index. This means that the referenced rows must be indexed, and they will be so because it should be the primary key of the table. But again, that's adding I/O, and it's taking more memory. So there is a cost. And also, an indirect cost is that there will be more logs inside the database. So let's go here again. If I try to, if I do an update for a project assignment, and then I want to delete the webinar, this project, what will happen is that this row is going to be locked, and until I don't complete my update on the related rows, this row will remain locked. So for the duration of the updates on the related rows, the foreign key, the parent table, will remain blocked because I cannot let this row disappear while there are ongoing operations with related rows. So that's adding locking, and I've seen many times how this will introduce deadlocks, and it will introduce a big amount of row locks, like simple row locks. If you are updating 1,000,000 rows, you are now locking 1,000,000 rows on this table and 1,000,000 rows potentially, or X amount of rows on the parent table. So it can add up quite quickly. The, and then it also brings some management issues. For example, the order in which you load the data. So you will have to first load the parent table and then the child table, because you can not insert into the child table until the rows exist on the parent table, because if they don't exist, then they are breaking referential integrity. And that makes things a bit cumbersome, to say the least. And if you have like circular dependencies, like if I have, you can actually self-reference a table directly. That's the easiest to explain. Like I can, if imagine you are trying to do a nested structure of files and folders, right? So you have your file ID and parent ID, and the parent ID must be a folder, but the folder could be inside another folder, and that will have, it will self-reference the same table to another ID. When you want to load that table, it's going to be damn hard. You cannot just reinsert the rows linearly. So what we normally do in those cases is to disable foreign keys to allow the table to load without the special procedures, because otherwise you will need to untangle the dependencies and insert top bottom. So you will need to insert all the parents first, then all the childs, then all the second level childs, and so on. So to prevent that, what we normally do is just disable foreign key checking for the duration of data load operations. That is quite common. And it should be totally valid if you already had foreign keys on the source of the data dump, because then the referential integrity is already guaranteed. And there is one more bit I forgot to put on my bullets, but basically we said you cannot delete from the projects table if there is still a project assignment for that project. Well, you can if we add as definition of the constraint, we can add a cascading effect. So we can say that on delete cascade, meaning that when I delete on the parent table, the delete will cascade to the child tables, and it will delete the rows that corresponded to the deleted parent. So if I delete ID 99 on the projects table, it will delete my row with project ID equals 99 on the project's assignment table. So again, this is done to guarantee referential integrity. I don't want to delete without deleting the other one. So there are two options. I either delete and cascade, or I fail the delete, and then the application will have to take care of deleting in the child tables. So this brings quite an issue sometimes. So use with care. And again, it is a very good idea to use it for critical data, right? Like if you have money or items that are, your inventory, like, okay, yeah, inventory, it's a good one. I'm not sure I will do it for a blog system and the comments, or for, I don't know, my agenda or whatever, right? Like I will try to use with care and not overload it, because again, it has a notorious performance impact. So, use with care, but do keep in mind this is the right way to guarantee data consistency among the tables. Okay, financial integrity, primary keys. This is also something quite important, and that people usually don't understand very well how important it is. So I'm going to talk about MySQL. Like, this webinar series is about MySQL, and within MySQL, like, we could talk about many storage engines, but I'm going to talk about the one that 99.5% of people cares about, which is InnoDB. So in InnoDB, primary keys are clustered keys. What does that mean? It means that the primary key will be a B tree, a B plus tree, and that at the bottom of the clustered key, of the primary key, in the so-called basement nodes or leaf nodes, we will find not only the value of the primary key, 15, 18, 20, 30, but we will also find the whole row for that primary key. So, primary key 15, it's employee ID 34, Bob. And then you have 77, Alice, and so on. So the point is that you don't have like a separate storage for the row like you will have in Postgres or you will have in Oracle, I guess. The key is part of the B tree. So they are one and the same. And this has some benefits and some drawbacks. The benefit is that when you're addressing through the primary key, you can immediately find, you already get the row. That makes primary key lookups faster. The drawback is if your row grows very big, you're going to have more basement pages, and that can be detrimental to performance. So, it's kind of hard to decide which model is best. But the important thing is to keep in mind the keys are clustered keys, and we want to have the rows in some order. In this case, they're going to be in the natural order of the primary key. So you can see that, for example, employee ID is not in order, right? But if I wanted to scan the range of primary keys, I can say, okay, give me any employee with primary key between 19 and 50, and I can very quickly, start here and here, because it's all always connected through the bottom nodes. And then a secondary key will look like this. For example, if I have a secondary key on names, my B tree will look like this: Alice Wusark, and then to the left I will have Alex, Eric, Rose, and then it will continue to split the tree, to branch out, and at the bottom I will have the primary keys. So Alice, it's oops, my bad, sorry for that. So Alice is 18, and I don't need the 77 was the employee ID, right? So I don't want that. I want the primary key, so that once I find the primary key, I can go back to the primary key and find the whole row. So I don't have pointers to the row on the secondary keys, but I have pointers to the primary key, which is itself the row. So that's one part about, like, keep your primary keys. So all the story about this is it's important to keep primary keys tight and light, right? Like to make it as lean as possible. And to understand how primary keys can become fat, I took a very common example, which is, should we use universal unique IDs, or so-called UUIDs, instead of an integer? Many people love UUIDs because they feel it's safer if you have distributed rights. You know, if I write here and I write here, and I use UUID, I will never have a conflict. That's true as long as you're only ever inserting data. As soon as you do deletes and updates, then God knows what's going to happen. So the certainty that primary keys using UUID, I will answer that question in a second. Please hold on, Amitabh. So the idea that having UUIDs as the primary key is going to prevent any and all conflicts, it's a lie. It's not true. It's an illusion. So don't rely on that. And here is why. It's not only not going to save you from the consistency issues, but it's also going to make your table much, much bigger. In this case, this example we are seeing here, what we are seeing here is a map of the age of table pages. So each table on my page has stamped the so-called LSN, the logical sequence number, which is a number that goes from 0 to 64 bits, which is many, many, many billions. And based on the logical sequence number, I can actually tell the age, how old a page is. It's not in days or minutes, but relative to the whole sequence number, right? And in this case, you can see on the bottom, my minimum is 38 million and my maximum is 342 million. So the blue is older and purple is newer. So the first 128 pages are the table header, and this is always going to be actively updated, more or less, but you can see there is some purple in the first few pages. That's because when you update the table and you add a new page, or or a page gets removed, you will have to update the file descriptor, which lives around there. So this first 128 pages, those are always updated, and they are again the table header. But then you can see, right, it's quite linear. And while here I have some red and then a bit of green, obviously there was an update that updated some rows here in line 384. It must have had an update. That explains why in line 384 I see some red before I see some green on 448. But the point is, it's growing forward, and if I want to read the last week of data or the last rows I inserted, if I only work with an active data set, I will only ever have to fetch pages from the last segment of the table. So it's not fragmented, right? What this basically implies, it's not fragmented, and the ranges of recent rows are easily accessible with few reads. I don't have to read the whole table to find the rows I updated today, which is a very common pattern in databases. I keep all my orders for the last 5 years, but actually only deal with orders from the last 2 or 3 weeks of sales. And I keep all the information for all the students of the past 20 years, but I only work with information of the students that are active this year. And so the time element in a database is quite important, and having the rows in having the pages that were last updated easily accessible in a sequence, it's going to improve performance. Let me answer the second questions. How the high DML affect the table structure? So yes, a large data modification query, if you do an update of all your rows, well, it depends on what the update is doing. Like I can think of, like, let's say I am adding, I have a blob column and I am adding or removing a lot of data. Then probably an optimized to rebuild the table will be in order. If I am only updating one column that it's a secondary, that it also belongs to a secondary key, then usually you wouldn't need to update it. Let me tell you this other ways. An InnoDB page, it's 16 kilobytes. And as long as you're not changing the size of the row so that it will, stop fitting inside the page, or such that it will now shrink so much that it will leave a lot of the page empty, then it's okay to not rebuild the table. What it's important is to rebuild the table after you do an update that will drastically change the size of the rows, because that will most certainly lead to fragmentation. So it's not mandatory to do an optimize when you do an update. Like if you're updating a date or you are updating an ID and you're not changing the size of those, then it's fine. If you are updating a string and you are changing the string from 10 bytes to 500 bytes, then probably it's going to end up creating a lot of fragmentation. So that you will want that. And this age map is created with a tool called InnoDB Ruby. It's from Jeremy Cole, which is a long-time contributor to the MySQL ecosystem. I will get you the link in a second if you don't mind me looking for it. Just 1 second, please. Jeremy Cole, InnoDB Ruby. Let me, okay, here it is. And how do I paste this on a chat? I will give it to my friend David, who will then share it with you, because I have no clue where the chat is here. All right. So, I private chat. I don't want private. I want to share with everybody. I'm very sharing person. Okay, I cannot find it, but my friend David is going to share with you in a moment. So again, you can see that for this table, I took less than 700 pages, and it's all neat and tightly packed. That's because the auto increments are, an auto increment ID, it's monotonically increasing. So it's always going to be filling up pages on the right side of the tree. And the way B trees are rebalanced is by pulling up one of these nodes later, right? Like once, like if the right side of the tree grows and grows and grows, you're going to have an unbalanced tree. So to rebalance, what you do is you pull up one of the nodes on the right to become the top, the one on the top. And that's the way you normally would rebalance the key, and that's why you want to always insert linearly on the right side. I see. Okay, no, I thought there was another question, but there were no more questions. So again, monotonically increasing keys will result in something like this. You could have ordered UUIDs. So UUIDs do have a date component. The definition UUID, I think, is the second segment, or who cares? But one of the parts of the UUID is a timestamp. So that's monotonically increasing. That's perfect. Now, it will still have 16 bytes. And it literally took almost double the pages in my table. So it's neatly ordered, but it's using much more pages. And remember one more thing. There is one more thing. Bigger primary key means bigger secondary keys, because remember, we have the secondary keys have the primary key embedded in them. So if you have a secondary key that is 4 bytes per row, and now you're adding like 16 bytes to that secondary key, instead of having a secondary key that will be 8 bytes, 4 for the secondary key and 4 for the primary key, you now have a secondary key that is 20 bytes. So as you add into the many millions of rows, these kind of small differences will start to add up, and they can make major impact. So yeah, you can have a UUID that it's ordered, and it will be neatly and tight packed, but it will be heavier. It will still have larger footprint on disk and in memory. And then this is the result of using a UUID without ordering, like without putting the date first, because this one is by chopping down the UUID and putting the date first, such that it will be ordered by time in a monotonically increasing way. This is the raw UUID, and you can see it got scattered all over the place, right? Like every page, it's permanently updated. So whenever I want to pull one of my pages, like imagine I inserted 20 rows today. To fetch those 20 rows, I only have to fetch the last page. But here, I'm going to have to fetch anything between 1 and 20 pages, because the rows ended up all over the place. That's the meaning of this. The purple is telling me the rows being inserted and updated are all over the place. I have to access all these, and each of these, it's representing IO. Like I have to go to disk to fetch the page, and I have to go to disk to write the page, and it's not the same page. So I'm going to have to do double the work, or X more amount of work, because I have to touch every page. And this is the worst thing, one of the worst things you can do for your database. It's like, it's causing fragmentation. Yes, it's very bad for the buffer pool, and it's very bad for your disk. It's literally, look, it's taking 2000, actually it's taking more pages. It doesn't even fit in here. But it's like my original database is taking 1, 2, 3, 4, 5, 6, 7, let's say 8 rows of pages, right? Like less than 400 pages, something like that, or 500 pages. This one is taking 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 14 rows, so let's say 800 pages. This is taking thousands. Again, doesn't even fit in the screen. So it's really one of the most detrimental things you can do for your database is using a non-ordered UUID. And if you can avoid it, just don't use UUIDs. Again, it's not saving you from anything, because again, it will only help you avoid conflicts if you only ever do inserts on the table. As soon as you do a delete on the table, you could be deleting rows from anywhere. And because again, this UUID frenzy comes from people that wants to have multi-master, because they have one node in Buenos Aires and one node in Montevideo, or they have one node in New York and another in San Francisco, and they want to be able to write locally to both. And so one way to say, okay, my primary keys are not going to conflict and I will be able to identify the rows uniquely, is by using UUID. But now let's say someone goes ahead and does delete from users where age less than 13, because we want to keep our kids safe. And then on the other side, someone says, update, I don't know, update allowance equal to something where city or where school name equals whatever. And you are gonna be touching the same range of rows on both sides, because you're not always accessing rows via the primary key. We many times will access rows via secondary keys. And as soon as you do that, you can have overlapping ranges on the two sides. And then there goes your consistency. Consistency is no longer true. So using UUIDs is not going to do anything for your consistency. So don't use them. Just don't do it. And yeah, a good guide to MySQL UUID functions. I will try to show you a neat trick in a moment. But let's finish this. And what about using unique keys as your primary key? Yeah, totally valid. That is perfectly fine. And as a matter of fact, InnoDB will do it. So let me explain this. InnoDB, we said a moment ago, it uses clustered key. So it basically cannot live without a primary key. So if you don't add a primary key, InnoDB will add one for you, and it's going to be 36 bytes. You truly don't want that. That's the worst thing you can do, is not add a primary key. That's probably the only thing worse than using a UUID key, is not using a key, because InnoDB is going to choose one for you. It's going to be a huge one. It's not monotonically increasing, and you have no control on it. So InnoDB, because it so desperately needs a primary key to actually store the rows somewhere. If you don't define a primary key, but you define a unique key that has no nullable columns, it will pick it up as the primary key itself. And it's totally valid. It's perfectly fine. You don't need to add extra columns to be the primary key. Make sure it's not huge. It cannot have nullable columns. And again, make the leftmost column, and I didn't put that here, I should have, make the leftmost column monotonically increasing. Because again, otherwise you're going to end up with the same problems than UUIDs. So yeah, unique keys are perfectly good. Just make sure they are not 300 bytes wide, because it's going to make your secondary keys very, very large. So, not a bad idea. It's perfectly valid. And again, InnoDB is going to do it for you if you don't define a primary key and you do define a unique key, but might be less than ideal in some situations. And then very quickly, because we're almost at the top of the hour, we're going to take a look at data types. Again, data types are the kind of they define data types will define a few things. Basically, what I have listed here, and which is the crux of the topic. First of all, it will tell, okay, is this a numeric data type? Is this a date? Is this a string? Spatial is for geo information systems. So geometry, line, point, etc. So they allow us to write queries to locate things on a map. Very important if you're into mapping stuff. And then JSON, which is a special type of a string. So first of all, we have those types. And then we have precision and storage requirements. So I can have a numeric type with more or less precision, or I can have a datetime with more or less precision. String will only have how much of a string, how big of a string I can store. Spatial doesn't have any kind of precision, and JSON either. And then storage requirements, and this is the most important bit. Every data type has different amount of bytes on disk. And if I store the number 123 on an integer, I will always use 4 bytes, even when I could have stored that on a tiny int that is only 1 byte. And this is really important. Again, when you are talking about many millions and billions of rows, then this becomes important. And again, your data type is not only going to be on the row, it's going to be on the secondary keys. And it's also will need to be referenced probably in other tables. So if I start using, I will believe this is the most common mistake people do. They go for big int. They use big int in their primary keys because, I will never run out of big ints. And you are absolutely right. Like big int is enough to count the ants on the earth. Should be enough to count the ants on earth. And I'm sure most people doesn't have ants as customers. So there is no point in having big int for your customer ID. And then you will have to reference your customer ID in 10 other tables. So you're wasting bytes, not only in one table, you're wasting bytes everywhere you reference the table. And again, it's not going to break things. It's just going to make your database perform less optimally. It's going to cost you more on storage, and it's going to cost you much more on memory. So choosing the right data types, it's important. And I realized, I will admit, I did these slides on a bit of a rush. And I stupidly forgot to add the example range. But for example, tiny int can go between minus 127 to 127. Or you could do an unsigned tiny int, which will go between 0 and 255. Small int goes between minus 3200, 767 to 32,768. And if you do unsigned, then it goes between 0 and 65,000, blah, blah. Medium int goes between minus 8 million to plus 8 millions, or if you do unsigned, it is between 0 and 16 millions. So using the appropriate data type is saving you everything you do. It's done with bytes, so if you're saving yourself a few bytes, you're saving yourself those few bytes from every single operation you do. Reading from disk, allocating memory, comparing, compressing everything you do. Everything you do is going to be done with this data. So as you shrink your data types, those operations are going to become more efficient and your database is going to run faster. So this is really so important that it's, hard to understate. And people tends to abuse data types and just use very big ones. They use varchar 255 for everything, and they use int and big int for everything. And it's a blanket. And I empathize. It takes time and effort to identify proper types, but it's worth the effort, especially if you're just starting and you can define the domain of your database from scratch. Do take the time, and you will enjoy better performance in the long term. And I don't have much more to add to that. So perhaps anybody else has some questions and we can stay a few minutes. Otherwise, that was my humble presentation about the schema design. How do I stop?
Let me get off mute. Something to reiterate, if you use big int for your primary key and that field's indexed, you have 2 big ints used for every record. And then you add a secondary index or 2. So suddenly you have 3 or 4 big ints out there, sucking up memory, sucking up disk space. And you do that a few billion times and things get messy.
Yeah, they do. They things like, again, where you were able to fit 2, because an int is 4 bytes. So where I was able to fit 2 primary key values, now I am only able to fit 1. Yeah. And you see, it's really costly.
Yeah, as someone who did a lot of his early career writing assembly language programs, that's always seemed rather obscene to me. But oh well. Let's see. We had a question from.
Yeah, I have seen Juka has a very interesting comment. So let me tell you something. We fully know it happens, but the limiter for unsigned int 4 bytes is 4 billion something. It's a big number, 4 billion plus. So there are 2 ways that this can happen. First of all, you probably didn't use unsigned. So unless you need to use minus, like negative values, make sure you always use signed, because perhaps you still have half the range to use and you just hit the limit at half the range. And the other one is, there are 2 more ways that things can go wrong here. One is if you use auto increment, and auto increment offset with somewhat large values, you're going to be leaving gaps in the range everywhere. So those auto increment, auto increment offsets, they were also meant to do multi-master replication to avoid conflicts. Like, I will write all my 1, 3, 6, 9, 12 here, and I will write all my 2, 4, like crazy stuff, like really crazy stuff. And what happens is, not only it's not going to save you from conflicts later down the road, like we said for UUIDs, the same is true for staggered primary keys in 2 nodes. Like, it's not going to save you from, like if you write all your odds here and all your evens here, you will stand up and end up with conflicts when you do updates or deletes via a secondary key.
Yeah.
And you are going to be leaving gaps. You will probably be leaving big gaps in the range. So you're depleting your range. So where you will be able to fit 4 billion rows, perhaps you only fit 500 million or 1 billion, and the rest is pure gaps. So don't use auto increment / auto increment offset. And the other problem could be with the InnoDB auto inc log type. So to avoid locking the auto increment, InnoDB does some complex trickery to allow you to do multi-row inserts and big insert select queries without having to lock it, but that will reserve chunks of the range, and then if something gets rolled back or the insert fails or whatever, the range might go unused. So InnoDB auto inc lock equals 2 could be causing your integer range to be depleted more faster. And I see you get posted another one. Usually problem is not changing primary from integer to unsigned int. Oh, yeah, changing related Java code. You're certainly going to have to deal with that, but that's a programmer's life, not that.
Yeah.
Just kidding. But yeah, I empathize that it will indeed require a UL type on the. So an unsigned large, I think it is. I think it's unsigned large. At
Yeah.
least that's what it's in C. I cannot recall what it's in Java. I'm very poor at Java, but yeah, data types and typed languages, they go hand in hand, and they can be messy. And yep, it will indeed. That's why ORMs are both a nightmare and a bless, because it's easy to actually save yourself from that.
Yeah, and programmers, make sure you check those return codes. You might assume that it's something went okay, but it's kind of fun to come back and have the system tell you, no, we're out of space, or no, there's a conflict, and have that ignored, and then come back 2 weeks later going, well, where's all this customer data?
Yeah, as a matter of fact, one of the checks we do, for example, in managed services, and that we are implementing for PMM is checking your ranges for the primary keys. Like, are you about to run out of primary key range? So we have that in as part of our monitoring, because we know it happens, and it's like devastating. So yeah, it's a very bad situation to be in. So monitoring that is important. It's part of the monitoring deal.
Yeah, as an analog, the Postgres world uses 32-bit integers, and their primary keys are 32-bit integers. And there are actually cases where if you're not doing your table maintenance, you run out of 32-bit integers, and suddenly nothing can go in the table. And one of the things that can happen is, in rare cases, it starts overwriting numbers, and all your old data is gone, and your new data is there. Well, it's not really gone. You can still get to it, but not really. You need a ninja level coder to be able to get to the stuff. So that's one thing that MySQL's clustered index does do for you, that you don't have to worry about.
Yeah, the data will be there at least.
Cool. So we had a quick question about the flame graphs that you were displaying. How did you get those?
Again, those were I gave you the link in Slack, in our Slack, because I couldn't put it in the chat here. I cannot find a public chat. I can only find the private chat. So
hold on, folks. I will get that out there.
Jeremy
Cole's Ruby thing. Okay.
Yeah, it's from Jeremy Cole. Jeremy Cole, it's a dear friend of Percona and a great contributor to the MySQL ecosystem. And he, as part of his own personal study into InnoDB, he wrote this tool along with a series of diagrams that I consult periodically, that they showed the layout of the InnoDB internals for the page, the row, the B trees, and everything else. Really great material. Like, you can check in his GitHub repo. There'll be one that is called InnoDB diagrams, I think. Let me see.
Yeah, by the way, this is the most ambitious Ruby project I've ever seen.
Yeah, the other one is called InnoDB diagrams, and it's literally all the diagrams that describe the storage format and layout for InnoDB. Super useful.
Cool.
Yeah. Well, again, that's where I will tell you, don't let Galera eat your auto increments. Disable, first of all, always write to a single node in Galera. Always write to a single node in Galera. Don't do multi-master in Galera. That's guaranteed to be free of conflicts, but in a sense that it will never store a row with a conflict, but it's going to roll back one of the transactions, and it's going to force you to write that transaction again. and that's going to cost you performance. And on top of that, then you're going to have to let Galera do your auto increment thing. Don't do it. Just write to a single node and disable. There is a WS rep auto increment control, or let me check.
I believe it's also the same information for InnoDB cluster, right? Run single primary, not multiple primary, write to one using like 4467 or whatever the port is, and let it handle that. The more you try to outsmart the software, the more you're going to set yourself on fire.
So I just asked Abe to share the name of the variable. It's WSRep auto increment control. That will tell Galera if it should deal with the auto increment, auto increment offset. My personal advice, is no, don't let Galera do that. Just use sequential 1, 2, 3, 4, 5, 6, 7, and write to a single node always. And if needed, use proxy SQL in front so that it can send the writes to a designated writer. And when that writer fails, it will pick another writer. But don't use WSRep auto increment control on. Disable it and make sure auto increment equals 1, auto increment offset equals 1, and you will have longer lasting integer ranges.
Okay. Well, thank you very much, Marcos, and thanks to our audience. If you do have questions or suggestions or stuff you want us to cover, please let us know. And with that, thank you all very much, and have a great day.
Have a good one, everybody. Thanks for attending. Bye-bye.